Hello students, welcome back to the session. Now let's continue, okay, from where we have stopped, okay. IL is equal to fifth point. Fourth point we have finished. Frequencies at which current through inductor and current through capacitor maximum, okay. We have seen some important formulas. We have seen the waveforms also, the diagrams, okay, the characteristics we can see. So here IL is equal to minus JBL by Y. It is just current division, right? So it is actually G plus JBC minus JBL, nothing but Y into Y into I. But complex form I'm taking. I'm not dealing with the magnitudes. We did the same thing in case of derivation of frequency at which IL and IC are maximum. There we have dealt with what magnitudes, but now I'm taking complex. Okay. So into I. See here Y is nothing but G at resonance. Yes or no? You also know that minus G, this is nothing but Q only, quality factor. Clear? So this is 1. Similarly, IC is equal to plus JBC by G into I plus J. Okay, this is Y actually. Okay, I told you already. BC by G at resonance plus J. This is nothing but again quality factor. You also know that at resonance, IR is equal to Y. Okay, so from this you can say IR magnitude is a very, very important observation. I magnitude, IL plus IC is 0, IR plus IL. Okay, IR plus IL. What is this? IR plus IL? I plus minus JQ. That is I minus JQI magnitude. Therefore, you know that Q is greater than or equal to 10. Since, therefore, IR plus IL is very much greater than I. Similarly, for IR plus IC. Okay, I'm just writing it down. Please note down. We already did this part in case of series resonance in a similar way. There we were dealing with voltage. Now here we are dealing with currents. So from this I can say IR plus IC. There was directly one question on this relation in gate. Exactly the same question. I'm going to discuss that part. Okay. From this we can say it's very, very important. Please note down. For all f less than fr, f increases, y decreases, z increases, voltage increases, current through resistor increases, inductive circuit. For all f greater than fr, f increases, then y increases, z decreases, v decreases, ir decreases, capacitive circuit. F is equal to fr, y minimum, z maximum, v maximum, IR is maximum. Resistive circuit. Clear? Very, very important to be remembered. Just summary, just before exam, if you just have a look at all this, you can answer many questions. Okay? Complete, all of you. This part you note down, and just meanwhile I remove. Third characteristics. Angle phi versus omega. I told you already to take I is equal to I at angle of 0 to compare both series and parallel circuits. Okay? Angle phi. When omega is 0, BL is infinity, BC is 0. It is acting like a pure inductive circuit. Therefore, you got it. The angle, how much here? Pure inductive means current should lag. That means it must be positive angle, plus 90. Omega is infinity, then BL is 0, right? BC is infinity, pure capacitive circuit. So angle phi will become minus 90. Okay? Omega is equal to omega R, then BL is equal to BC. Pure resistive circuit. Angle phi will become what? 0. If you draw the characteristics, plus 90, minus 90. It starts from plus 90. This is omega R. Angle phi versus omega. Omega R is acting like a leading power factor circuit. Here it is acting like what? Lagging power factor circuit. Whereas here, unity power factor circuit. Please note down. Okay, so if you look at this now, this particular case, I think we have done the same thing in case of series also. Okay, when you have drawn the characteristics for Z versus omega. Now here Y versus omega. Okay, there we have drawn Z versus omega as well as Y versus omega. Here we have drawn Y versus omega, but we did not draw for Z versus omega. Okay, so please place the same thing at that first characteristics. Okay, first characteristics, you do the same thing over there. So omega is equal to omega R. Okay, first characteristic I'm talking about. I think you have seen first characteristic something like this, right? Okay, you have done like this. There itself, okay, there itself, you please draw these characteristics. These characteristics. So y becomes what? Here the g value, if r value is or g is equal to 0, nothing but what r is equal to what? R is equal to infinity. Understand? So y is equal to 0. Then z becomes what? Infinity. It becomes what? Resistive. Clear? So when you draw the characteristics here, look at this, all of you. This is what the frequency at which resonance occurs. Now when you draw the characteristics for z, understand? When you draw the characteristics for z versus omega, when you draw, initially it is inductive. For z to be inductive, because it starts from 0, but is inductive, that means it's the first quadrant or fourth quadrant. When it is inductive, the impedance characteristics will be in first quadrant. When it is capacitive, impedance characteristics are in fourth quadrant. Yes or no? So therefore, first quadrant you will have 0 it starts with. Understand? This is now inductive. Okay? And it goes to what? See this? When omega is reaching from 0 to omega r to infinity, impedance is reaching, okay? Impedance is reaching 0 to infinity to again 0. It's a very, very important observation. Clear? Okay. So it starts from here. Okay, infinity, it starts from infinity. All of a sudden, because up to this, the frequency reaches omega r, then it goes up to infinity. Then all of a sudden, from infinity to it enters into what? Capacitive. So therefore, it's a capacitive circuit. Clear, all of you? Okay, it's a capacitive circuit. Right. So this is now capacitive circuit. Clear, all of you? Okay. So please note down the same as it is the question has been given in the GATE examination. I am going to discuss that question also. Please note down this. But please note all these things at the place of what? Z versus omega. There we missed it. So please place the same thing over there. If you find some place. If you don't find some place, write as it is. Okay. Please quickly note down. Now let us look at the problems in the classroom workbook. Question number 1. Question number 1. Classroom workbook in the topic resonance. Let us look at the question number 1. Okay, let me read it. In an RLC series circuit, applied voltage 10 at an angle of 0, R is equal to 5 ohm, C is equal to 20 microfarad with a frequency of 1000 radian per second, and L is adjusted until the voltage across the resistor is maximum. Find the voltage across each element. Okay, so I think you have this question with you. Please refer that question number 1. Okay, what is given? Actually, the applied voltage V is equal to 10 at an angle of 0 is given. Resistance R is equal to 5 ohm. C is equal to 20 microfarad. And L is adjusted until that VR becomes maximum. So he's asking what is the voltage across each element. Okay, so it's very simple question. See, most of the times when the problem is given in resonance, it doesn't mention directly that problem belongs to resonance. He will give you some indirect information. From that, you have to understand whether it belongs to resonance or some other problem. Okay, look at this. VR maximum, RLC circuit, L is adjusted. VR becomes maximum means what? VR is equal to I into R. R is independent of L value or frequency. Therefore, VR is directly proportional to what? I. So when VR is maximum, then I is maximum. Yes or no, all of you? Then Z is minimum. All are resonance conditions, right? When do you get Z min? Tell me, all of you. Only at resonance. Yes or no, all of you? When do you get I max? When do you get VR max? All are happened only at resonance. It indicates that the condition for resonance is given, or resonance, the circuit is in resonance is saying. So L is adjusted until the circuit is, becoming resonance, okay, becoming resonant. So therefore now you know that at resonance, you know that VR is equal to V. Yes or no? So what do you get here? 10 volts. So one voltage is known now. At resonance, you know that VL is equal to now I into XL. But what is I at resonance? But I at resonance is, okay, V by G. V by what? Z. But not V by Z, it is V by R. Okay. What is V actually? 10. 10 by 5, simply 2 amperes. So therefore, so VL becomes what? I is nothing but how much? 2 amperes. Into XL is how much here? It is not given. Yes or no, all of you? It is not given. But do you know what is XC? The frequency was given, right? How much frequency was given? 1000 radian per second. The frequency was given 1000 radian per second. So I guess you can find first XC value here. So what is XC none? Or else VC is equal to I into XC, right? I into XC. And both are same actually. VL is equal to VC. So let me find first XC here. What is XC? 1 by omega C. 1 by, what is omega? 1000 RPM, radian per second, into C value, 20 into 10 power minus 6. Getting all of you, okay? So I guess you get, this is 4, 200 by 2, that is 50 ohm. If XL is equal to 50 ohm, then XC is equal to 50 ohm, then XL is equal to XC is also 50 ohm. Now VC is equal to I into, that means 2 into 50, that is 100 volt. When VC is 100 volts, then VL is also equal to what? VC. Also 100 volts. That's it. He's asking what is the voltage across each element. Okay. So please note down. Very simple. He will give you indirectly the information. Please note down quickly. We'll move on to another problem. The question is given, determine the frequency for which the following circuit is resonant. Determine the frequency for which the following circuit is to be resonant. Okay, so he's just asking what is omega R of this particular circuit. Understand? See, in the exam, he will give you all parameter values and he may ask you to find the resonant frequency. Sometimes he may give the resonant frequency and he will miss any one of these parameters and he will tell you to calculate that parameter for which the given circuit is resonant at a particular frequency. There are two varieties of problems you come across usually. Okay. So now, for all these kind of problems, there is a standard procedure. You know that resonance condition for resonance is always what? Imaginary part of input impedance is 0. Imaginary part of input admittance is 0. Phase angle difference between voltage phasor, current phasor is 0. Yes or no? Power factor of the whole circuit is unity. All are same, right? So let us make use of imaginary part of input admittance is 0 condition because it is a parallel circuit. For a parallel circuit, always better you deal with admittance. For circuit to be resonant, imaginary part must be 0. So first of all, let me check out here. What is Y? Y is nothing but 1 by R minus jXC plus 1 by R plus jXL. R plus jXC by R square plus XC square. r minus j xl by r square plus xl square. You know that r by r square plus xl xe square plus r by r square plus xl square. Yes or no? Plus j xe by r square plus xe square minus xl by r square plus xl square. You have to make this imaginary part 0 for the circuit to be resonant, for resonance. Okay, so first problem I'm just writing in detail. Okay, so next time onwards you can do it easily, right? Imaginary part must be 0. That means xc by r square, rl square, right? So what is this actually? RL. Okay, RC. This is RC, this is RL. So please correct it. RC, RC, RL, RL. RC, RL. RC, RL. Clear? Okay. So RC square plus XC square, right, is equal to XL by RL square plus XL square. Now you can find it out, right? So RL square XC plus XC into XL square is equal to XL into RC square plus XC square into XL. Is it clear all of you? Okay. Now what you do is you substitute in this. You substitute in this. This is XC XL square and XC square XL. Is it clear all of you? Okay. This is XC and XL. This is RL square XC. This is XL into RC square. So in this, if you substitute, XC is equal to 1 by omega RC and XL is equal to, understand? Okay, omega RL. If you substitute this in equation 1, this is equation 1, let us say, then you get entire equation in terms of what? RL, RC, omega R, L and C. Understand all of you? Okay. So finally, substituting this in 1, then will give you omega R. I am directly giving that. Okay. Root LC here. Root. Okay. RL square minus L by C by RC square minus L by C. This is very, very important. Okay. Understand all of you? Okay. The numericals are given, then it will be easy to find. Then if you substitute that RL square minus L by C and RC square minus L by C. Getting all of you? Okay. The procedure is very important. You can't remember this formula and then solve any problem that you come across. It's not possible, I'm telling you. Every problem must be done always in that manner. Otherwise, it's a time-taking procedure. You can't remember. If omega R is asked and all the values are given, then it's okay. But if omega R value is given or any one of the parameters is asked, I'm sure that this formula won't help you. Again, you have to do from the beginning and then you have to work out on that. Clear? So this procedure is very important. Whenever is asking any parameter under resonance, always find, if it is a parallel circuit, find admittance, separate real and imaginary, make the imaginary part 0. Proceed the same way I'm telling you. Okay. Note, this is very important. If RL square is equal to RC square is equal to L by C, in case if you design like this, then the given circuit is resonant at all frequencies. Understand all of it? That means at all frequencies it is resonant means what? Omega equal to 1 radian per second it is resonant, omega equal to 2 radian per second it is resonant. That means what? The circuit is resonant for all frequencies means the entire circuit is independent of frequency. Yes or no? Even if you change the frequency, okay, at every frequency it is becoming resonant means, okay, even if you change frequency, there is no change in the condition of that resonance in the circuit. Therefore, you can say, okay, the given circuit is Okay, please note down, that's very, very important. In exam, you can expect some questions on that particular condition. You have to remember that condition. Clear? I guess you have finished this, right? I move on to now let's look at the third question. Determine the frequency at which the following tank circuit is resonant. Okay. Determine the frequency at which the following or the given tank circuit is resonant. This is called tank circuit. What is tank circuit? When a practical inductor is connected parallel to an ideal capacitor, that is called a tank circuit. Tank circuit is nothing but a practical inductor is parallel to an ideal capacitor. Right? Okay. The practical inductor is parallel to an ideal capacitor. Understand all of you? If an ideal inductor is connected to ideal capacitor across each other, that means parallel, then that circuit is called a ideal tank circuit. This is a practical tank circuit. A practical tank circuit, an ideal tank circuit. What is ideal? If RL is 0, then it becomes ideal tank circuit. Understand all of you? Okay. Well, now what is asking? Let's come to the point. Omega R of this particular circuit. Procedure is same for a parallel circuit. Y is equal to 1 by RL plus JXL plus 1 by minus JXC. Again, you separate real part and imaginary part and make this imaginary part 0. Understand all of you? And substitute. Okay? And substitute. XL is equal to omega RL and XC is equal to 1 by omega RC. This is a standard procedure. This is a standard procedure, I'm telling you. Okay? So therefore, when you substitute here, you will get, I'm telling you, I'm giving you directly the answer, root. Let's see. I'll give you that answer directly here. Yeah. 1 minus R square C by, yeah. Okay. This is also noted as LC of 1 minus 1 by quality factor square. You know that what is the quality factor, right? So quality factor is actually 1 by R root L by C. So from this Q square is, okay, 1 by R square L by C. So from this 1 by Q square is R square C by L. So from that you can determine easily. So this is very, very important expression. So what is the procedure again? So, rationalize, separate real and imaginary, make imaginary part 0, substitute XL is equal to omega RL, XC is equal to 1 by omega RC, you get omega R value. Please do this part at your free time, you will get that answer. Okay? Quickly note down. I'll move on to another problem. Note. Dynamic impedance of a tank circuit. Dynamic impedance of a tank circuit. Dynamic impedance. Right. So, first of all, let us try to understand what is the dynamic impedance. What is dynamic impedance? Okay. See, in any given circuit, if you have RLC elements at a particular frequency or a particular variation of a particular parameter, let us say the circuit is resonant. Understand? When the circuit is resonant, that inductor reactance, I'm just analyzing it with respect to RLC series circuit to make you understand. The same thing we apply to a tank circuit also. That's not a big deal. Okay. So for a series circuit, what is that? XL is equal to what? XC. What is that? QL is equal to what? QC. Understand all of it? Okay. QL is equal to QC. That means the net reactive energy, that net reactive power or energy, okay, reactive energy supplied by the source is zero. Yes or no? See, there is an inductive reactive power demand and capacitive reactive power demand, but still the source is not supplying. Usually when you connect a resistor, the source will meet the requirement of the demand, that is active power demand. When you connect a reactive element, the source has to meet the demand of the reactive power. But here, both reactive powers are there. We have inductive reactive power as well as capacitive reactive power. So when you have the reactive power, QL is greater than QC, that means XL is greater than XC, then QL minus QC. That means whatever the reactive power demand is there, that QL, a part of it is met by what? Capacitance. That means capacity is able to meet some part of the demand of the inductive reactive power, but the remaining reactive power is supposed to be supplied by the source only. How much? That is QL minus QC, the remaining part. Similarly, when you have QC greater than QL, same way, QC minus QL is the remaining reactive power. Demand is supposed to be met by the source. But when you have QL is equal to QC, now inductive reactive power demand is met by capacitive reactive power, and capacitive reactive power demand is met by the inductive reactive power. Then what is happening here? There is a continuous exchange of reactive energy between inductor and capacitor. Understand all of you? Okay. When there is a continuous exchange of reactive energy between inductor and capacitor, or when there is a continuous exchange of, or when there is a continuous transfer of reactive energy between inductor and capacitor, okay, first half cycle it goes from inductor to capacitor, let us say, then second half cycle capacitor to inductor. It is continuously taking place. Therefore, this scenario is called dynamic. Then the circuit at this particular scenario is called dynamic. Understand all of you? When there is a continuous exchange of reactive energy or power between inductor and capacitor, then the circuit is said to be dynamic. Understand all of you? Okay. The impedance offered by the circuit at this situation is called dynamic impedance. Now you tell me, how did you get this dynamic condition? Is it not because of XL is equal to XC? Is it not because of QL is equal to QC? Yes or no, all of you? That means what? Resonance condition. That means dynamic impedance is nothing but what? Impedance offered by the circuit at resonance only, nothing else. Getting all of you? Okay. So please write on this. Note. 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 At resonance, the net reactive power or energy supplied by the source is zero. At resonance, the net reactive power or energy supplied by the source to the circuit is zero. To the circuit is zero. That means though there is a demand of inductive reactive power and capacitive reactive power, that is, though there is a demand of inductive reactive power and capacitive reactive power, the source is not supplying any reactive power to the circuit. The source is not supplying any reactive power to the circuit. Okay? Full stop. There is a continuous exchange of reactive power between, or there is a continuous transformation of reactive energy between, reactive power between inductor and capacitor. There is a continuous transformation of reactive power between inductor and capacitor. There is a continuous transformation of reactive power between inductor and capacitor at resonance, and the circuit is said to be dynamic. And the circuit is said to be dynamic. And the circuit is said to be dynamic. Okay, that means what? Any resonant circuit is a dynamic. Understand? Okay. The impedance offered by the circuit at this condition is called dynamic impedance. The impedance offered by the circuit at this condition is called dynamic impedance. Clearly written, all of you? Well, now look at this. For a tank circuit, there is a simple procedure, phasor diagram approach to derive that dynamic impedance. Very simple. This is RL, L. Okay. So you have, let us say, this is I, this is V, let us say. This is I1, let us say, this is I2. Say this is Z1. Okay. Z1 is RL plus JXL. Theta, angle theta. This is RL, this is XL, this is Z. Clear, all of you? Okay. Well, let us take a phasor diagram approach. Let me take V is equal to V at an angle of 0. Because of parallel circuit, I am just assuming. And I am sure that I1 is I1 at an angle of theta. Clear? Is it lagging or leading? Lagging. Yes or no? So therefore, you will definitely have minus theta. I2 is, okay, definitely you will have the angle. How much angle you will have? Tell me. I2 magnitude at an angle of, okay, plus 90. When you compare with this, because voltage V, and it makes an angle what? Plus 90 only. Now if you draw that phasor diagram, V, this is I1, right? How much angle it is made? Theta. And this is what? I2. How much angle it is made? 90 degrees. Clear, all of you? Now at resonance, let us try to find the impedance of the circuit. Getting all of you? At resonance, we'll try to find the impedance of the circuit. At resonance, what will happen? Tell me, all of you. This particular path is having two components of the current. One is a real component, the other is what? Imaginary component. Horizontal component, vertical component. Real component, imaginary component. But this current is having only imaginary component. Now this I is nothing but I1 plus I2, nothing but what? The real component of this and imaginary component of this. The imaginary component of this. All these together is what? I. Now the circuit is said to be in resonance if the phase angle difference between voltage and current is 0. it is possible only when this I is having a real component, no imaginary component, because already is making a 0. Now the current should also have angle 0. It is possible only when it doesn't have any imaginary part. Understand all of you, okay? Suppose if the imaginary part of this and imaginary part of this both are getting cancelled, because I is equal to I1 plus I2, imaginary part of this and imaginary part of this got cancelled, then what will happen? Definitely I will be having what? Only real part. Yes or no? All of you? Therefore, you see this now. You see this now. This is what imaginary part. What is this? I1 sine theta. Vertical component. What about this? Horizontal component. What is this? I1 cos theta. Okay. Now what is I actually here? In case if I2 is equal to I1 sin theta both got cancelled, what is the total I, Nana? I is nothing but I1 cos theta only. Yes or no, all of you? I1 cos theta, I1 sin theta and I2. All these components are there in I, but if these two got cancelled, then finally what is the total current? It becomes I1 cos theta. That is in phase with what V. The angle difference becomes 0. Then the circuit is said to be resonant. It's very, very easy to understand from the phasor diagram approach. Understand? So I'll do now one thing, that first condition for the circuit to be resonant, it must be I1 sin theta. Once it is I2 is equal to I1 sin theta, no doubt I becomes I1 cos theta. Is it clear? Well, what is I2? V by Xc. What is I1? V by Z1. Clear? What is sin theta? What is sin theta? What is sin theta here? XL by Z1. Clear all of you? XL by Z1. Got cancelled. And Z1 square is equal to XL into XC. Nothing but L by C. Yes or no? So finally you got Z1 is equal to root L by C. Right. Now here you can see I is nothing, okay, I remains same, but V by what? Z1. Cos theta is nothing but what? RL by Z1. Yes or no? Okay. But you see from this you can say V by I, that is the total impedance. Impedance is nothing but what? Or RMS voltage by RMS current is nothing but the impedance, right? So Z1 square by RL. Understand of you? This one is called Z, and at resonance condition you're applying, therefore you call it Z dynamic. Okay, nothing but what is Z1 square actually here? L by C, therefore L by, okay, C into RL. This is called dynamic impedance. Understand all of you? Okay, this is called dynamic impedance. It's very, very important expression to make. You may get direct question on this on formula basis. Okay, in case of ideal tank, that means RL is equal to 0, then Z dynamic will become what? Infinity. Dynamic impedance of an ideal tank circuit is infinity. It means that it is acting like what? Open circuit. So an ideal tank circuit behaves like open circuit. Okay, behaves like what? Open circuit. It's very, very important. All of you please note down. It's very, very important. Let us look at the fourth question. Find L in the following circuit such that the circuit is resonant at 5000 radian per second. This is the question given. Okay. So let me draw the circuit. I think all of you have that question with you. Okay. So this is what the circuit given. Okay. So standard procedure again, just don't by heart that formula and apply here. It's not possible because L is given. L is asking. He has given omega, but is asking L. Okay. So again, Y 1 by 2 plus JXL 1 by 5 minus J10. Okay. So you have the imaginary part. What is that imaginary part? Minus XL by 2 square plus XL square plus what is this value? J when you take common 10 by 10 square plus 5 square. What is 5 square? 25 plus 100. 125. Right. So 10 by 125. That's it. You have to make it 0 now. So when you make it 0, you will get now minus 125 XL. Yes, sir, no? Minus 125 XL plus this is 4, that is 40. 40 plus 10 XL square is equal to 0. From this you will get XL value. From this you will get L is equal to XL by omega. Okay. Then you will get the values. Okay. So please do that calculation. I'll give you that values here directly. You can cross check. Use the calculator. Don't do any mistakes in the calculation part. Don't do silly mistakes. Okay. Minus 125 XL plus 40 plus 10 XL square. Okay. So you will get XL value, that is 12.17 ohm or 8.35 ohm. Then L will become 2.434 millihenry or else 1.67 millihenry. Understand all of you? Okay. So this is how you calculate L value. Fifth question, you can see. Fifth question. At what value of C the power transmitted to 10 ohm resistor will be maximum? Fifth question. It's very, very important again. Okay. Five plus J3 ohm and 50 at an angle of 0 volt and 2000 hertz. It's just asking at what value of C the power transferred to the 10 ohm resistor will be maximum. So power maximum. Generally, when power maximum condition is given, we may feel that the problem may come under maximum power transfer. Okay. But remember, for maximum power transfer, if you want to transfer maximum power to 10 ohm, it should not be fixed value, it must be variable value. Understand all of it? Okay. So here, that maximum power transfer condition theorem does not work in this particular condition. Understand all of it? Okay. But how you need to deal with this problem? Power of 10 ohm will be maximum when current through 10 ohm is maximum, when total Z is minimum. Total Z is minimum only in resonance condition. It is possible only at resonance. Understand all of you, okay? Only at resonance. This is RL, this is RC, totally RLC circuit. Then definitely XC must be XL, then only it is possible. Understand all of you, okay? So what is XL now? Tell me. 3 ohm, right? So 3 ohm, 1 by 2 pi FRC is equal to, or FC is equal to 3. And from this, you know that 1 by, okay, that is C value. You have to find the C value. C is equal to 1 by 2 pi into 3000 or 2000 heads into 3. Understand all of you? Okay. So this is how you have to solve the problem. I'll give you the answer directly here. C is equal to XL is equal to XC or XC is equal to XL. XC is equal to 3 ohm. And you have that value, C value, 26.525 microfarad. This is what your answer is supposed to be. Okay. Fifth problem, I'll stop here. In the next session, we will continue from sixth problem. Okay.